Hey everybody, Stacy here. Little video on electric charge. A couple demonstration videos that I'm going to play in a second, and then show how we can kind of model those with our ideas of the positive and negative charges that are inside objects and all the atoms that make up everything. But first, just a little background info. The name electron comes from the ancient Greek word electron, which was the name of amberglass or amber, fossilized tree sap that would be used for making jewelry was one common way. It's still used in jewelry now, I think. And that jewelry, when people would wear this amber, it could rub against their clothing, and it could generate an electrostatic potential. It could generate an electric charge that could then discharge in the form of an electric shock. And you experience that frequently. You can experience that in the wintertime around here when it's not as humid. If you're wearing a wool sweater or something and get out of the car, you can get an electric shock touching the metal frame of the car when you, say, close the door or something like that. That's why they have warning labels on gas station filler pumps. They say discharge all your electrostatic potential, so that you don't accidentally have an electric discharge while you're around flammable fumes of gasoline, because those could ignite it. You get the same sort of thing when you rub, say, the rubber of a balloon on your hair. You can generate an electrostatic potential, and you can see that as the strands of hair on your head are attracted to the balloon. And you can also place the balloon like up against a wall, and it'll stay attracted to the wall because the balloon has some sort of electrostatic potential that was generated just by rubbing it on your hair. And what happens in there is basically you have electrons that are moving from one object to another, and so those objects become charged. If you lose electrons, then the object's going to become positively charged. If it gains electrons, it's going to have an excess or extra electrons, and it's going to become negatively charged. And all that wording from electron down to electric comes from our original observations thousands of years ago with this stuff, amberglass. So we got a couple examples I'll show in a moment. What we have on the screen right now are just some of the basics of electric charge that we should know. We call the smallest amount of charge there is the elementary charge, so that's just a charge of 1. And the electron has an elementary charge -1, and the proton an elementary charge +1. The neutron is neutral, of course. And we say charge can only exist in discrete amounts, meaning these integer values 1, 2, 3, 4, 5, 6, or if we're saying -1, -2, -3, -4. You can't have 2/3 charge, 1/3 charge until you're talking about stuff smaller than the nucleus. So like quarks can have that stuff. But for the slightly larger scale, everything's just incremental, integer, discrete amounts of 1, 2, 3, 4, 5, etc. of charge. The total charge in a system is always conserved. So charge isn't being created or destroyed, it's just moving around. The electrons are the particles that are moving around. So we don't say the protons are moving to another object. It's really just the electrons in the outermost shells of the atoms that are able to move. Sometimes certain materials will let their electrons move more easily. Metals will do that. Other materials will not let electrons move so easily. We measure electric charge in coulombs, and we'll see Coulomb's law later in a different video. So that's the unit for charge. 1 coulomb of charge is a lot. Conductors are really good at allowing electrons to move freely throughout their material. Most metals are very good electrical conductors. Electric charge always spreads out equally and uniformly around the surface of a conductor. So here's the coffee mug. If I were to charge this up, if this metal is a good conductor, and I were to somehow get some electrons on it, they would all spread out uniformly because they're repelling each other. They don't want to get close to each other, so a conductor will let them move freely around, and so they'll all spread out uniformly. An insulator does not do that. An insulator doesn't let electrons move around very freely. They're kind of stuck where they are. You can put more electrons on an insulator, like the example would be of, say, a rubber balloon. If you rub that on your hair, you're able to get some electrons onto the surface of the balloon, or a piece of plastic. Those electrons are just going to stay there. So like here's the let's use my phone. Right, here's just some plastic. Can we see that? Right, the plastic casing on the outside. If I were to get some electrons right here by maybe rubbing it on my hair, those extra electrons are just going to stay in that region. They're not going to be able to spread out uniformly and cover the full surface of the material because it's an insulator. It simply does not allow the electrons to move freely. Triboelectric charging is the name for the process by which you can rub two things together and you can get electrons to move from one object to the other object. So again, with the example of like a balloon and your hair, by rubbing those things together, I can have electrons leave my hair, or maybe the case of my phone. I do that, and I get some electrons that have moved from my hair onto the case of my phone, and so we have, what was that? Something's flying around. So I'd have extra electrons on the surface of the phone, so it would become net and negative, we would say, and then my hair lost some electrons, so now it's net positive. It's positively charged. The same total number of charges, the same total number of electrons are still there in the system of my hair and the phone. They've just moved, and it's only the electrons that have moved. The protons aren't moving, the neutrons aren't moving. We still have the same total number of electrons as before, but by triboelectric charging, you rub something together, and you can get the electrons to move, so that one object can be negatively charged, say the case of the phone, the other object, like my hair, can be now positively charged. But everything's still conserved. All right, so let's take a look at a couple of the demonstration videos that I have for two kind of weird phenomena. There's also a video link that was posted in the kind of class materials for this week of 9 interesting little demos for electrostatic charge. That's good to look at. 2 of them are the ones that I'm actually about to do now. So we'll look at those and we'll come back. Okay, so in this one we've got, I got a regular soda can. It's neutral, it's not charged up, but I'm able to make it move, roll back and forth with this PVC pipe. So something's going on where I've just taken the PVC pipe and rubbed it against a wool sweater, a jacket, and that's done something similar to the amber glass being rubbed on clothing or something that I mentioned earlier, where there's some sort of buildup of charge on one of these objects. So there's a buildup of charge on this PVC pipe, and I'm able to actually make something move with it. Right later you can take this and figure out how to make a motor out of it. But right now it's just able to make the can roll back and forth. If we get a kind of a model, an image of it in this little simulation, there's a neutral aluminum soda can. And put a rubber rod there that tends to get negatively charged when it's rubbed with something. Rubber, each material is different. Some materials are more likely to get negatively charged when they're rubbed with another material. Other objects are more likely to lose electrons and become positively charged. So you can see in this little demonstration here, in the simulation, the aluminum can is neutral. There's the same number as negative signs as positive signs, same number of electrons as protons in there. But the negatively charged rubber rod pushes the electrons away, and you get a side of the can that's more negative and one side that's more positive. Here, glass tends to become positively charged, so when I put the glass rod on one side of the aluminum can, all the electrons coast over to that left side. They want to be by the positively charged glass rod, or if you put the rubber in there, the electrons move away, and so the can's attracted to the negatively charged rod because the positive charges of the nuclei want to go to that rod. Now here's an electroscope. You can call it. It's just two pieces of aluminum foil that are really thin. They're conductive a bit. There's a metal rod going straight down into the flask, and this metal sphere attached to the top. So they're all that stuff straight down the center is conductive, meaning it will really easily let electrons flow through it. So the leaves down at the bottom inside the jar, more or less just hanging there. They're inside the jar because the wind would just blow them away, so it keeps them isolated. I charge up this PVC pipe by rubbing it on my jacket. I'm not touching anything, but just bringing that pipe close to the electroscope. We can see that the leaves at the bottom move apart. As I get closer and closer, they move further and further apart, but I'm not touching the top of that flask. I'm going to come from the other side just so you can see that I'm not touching it. As I get closer, they move further and further apart. Now, I have to keep rubbing onto the PVC pipe with the jacket to put more electrons on there because it's actually discharging into the atmosphere fairly quickly. Now I've touched the top of the electroscope, that metal sphere, with the PVC pipe, and I'm literally wiping electrons off the PVC pipe and onto the metal sphere. The conductive metal sphere it has a larger affinity for electrons. Electrons would be much happier to jump onto that metal. So they jump on there, and now the leaves stay permanently spread out. When I touch it, the electrons have a place to escape. That's called grounding it, and so they leave the electroscope's leaves and travel through my body to the ground. I got another plastic rod here that's not charged up. I can continue to ground the electroscope till all the excess charge is out of the electroscope. And see, now bringing this neutral plastic rod towards the electroscope doesn't make the leaves do anything. I would have to charge it up and then bring it close again. Here's a way you can visualize it. Here we've got a rod that's being brought close to an electroscope in the simulation. It's a positively charged rod, so it's pulling the electrons up out of the bottom of the electroscope, and that's causing the leaves to move apart. As you move the rod away, the electrons can spread back out again, and this is a basic way to try and model that. You can also just look at a regular conductive sphere. So this is like a metal sphere that's isolated from the ground, and by moving a positively charged rod around, you can actually get one side more negatively charged and the other side more positively charged. That's what we call polarization. Same thing that's happening with that soda can. When you have one side of a material that's more negatively charged and the other side more positively charged, and yet the whole material is still neutral, we call that polarization. There are many molecules that can behave this way. Water is one of them that is actually polar. It has one side of the molecule that's more positive and the other side that's more negative. It's net neutral, though, as a compound.